Yeah, don't have any physical things to show you the concepts.
Just wave your arms, you know.
Huh? Just wave my arms to show waves.
Yeah.
If I were any good at it, I'd consider it. All right, so our second chapter now, focusing on waves. Told you that this was going to be one of the hardest chapters, not necessarily because the math is just so out there or the concepts are just so out there. It's because we're going to be talking about physical phenomena and modeling it two different ways, still using waves. And I'm afraid that you're going to get confused when we model it one way versus another way, which is why I strongly recommended you read this chapter, get the intuition there. So since you guys already did that, I know this is just going to be a breeze, right? 15.4. All right. But before we got into waves, I feel like last time I didn't make clear enough how we're changing how we're using omega versus how we are used to using omega. Angular frequency versus angular speed. I don't feel like I did a good job helping you guys understand what the difference was. So I thought we'd come back, and it's even just a good recap, redo a pendulum problem. I may have do the same pendulum problem that we did last time, but just a little bit different.
Okay.
The equation's going to come out the same, but going to do it a little bit different. So that you can see the difference between how we're using omega, starting with chapter 14 and later, versus how we were using omega in the past.
So we're never going to use it like we did in the past?
You could. We'll see what we mean by it. One's just called angular speed, one's called angular frequency. They're they're related. But anyways, let's go back to just a basic pendulum problem, the kind of thing that we saw last week. So I've got some pendulum here, and it's swinging back and forth. It's some mass m on some string of length L, and it reaches out some angle, traces out some angle theta, right?
Mm-hmm.
And we're going to assume that theta is always much smaller than 1 in terms of radians, which means always much smaller than 60 degrees. So swinging back and forth, and that's like 15 degrees, something like that. Good with the physical scenario we have here so far?
Yeah.
F is a restoring force, bringing that pendulum back to equilibrium. X is the distance along this path that it's marked out. With me so far?
Yeah.
Okay. So if we were to draw a free body diagram on this thing, we have mg pulling down, right? Mg is a force of gravity pulling down. We have tension in the string pulling this way. And then the tension and mg cancel out, leaving this restoring force. So tension cancels out some of gravity, tension cancels out this component of gravity, and so now there's still just this component of gravity, which is the same as F. So F is a component of gravity in that direction. The component of gravity not canceled out by string, which makes perfect sense. Gravity is what makes the pendulum swing back. If I pulled out a pendulum and turned off gravity, it would never swing back.
Okay.
All right? So F, and now what is the restoring force F? It's mg sine of theta. Right?
Yes.
Okay. And then negative, since it's in the opposite direction as our displacement.
So x is positive?
So if we call that way our positive x direction, then the force is in the negative direction.
Okay.
So our force is negative mg sine of theta, right?
Yeah.
Now, last time we didn't solve this using torque, so this time I'm going to solve it a little bit different, and we're going to use torques this time. Rather than F equals ma, we're going to use the fact that torque is equal to moment of inertia times alpha. But anyways, so what is the torque produced by this force? The torque produced by that force is equal to the length, how far away the force is being applied, times the component of the force perpendicular to our radius.
Perpendicular to your radius?
Yeah, and the whole force is perpendicular to this L, to this displacement.
Oh, I see.
Right? So it's completely perpendicular. So it should be L times F sine of phi, where phi is this angle, but phi is 90 degrees, sine of phi is 1, so it's just L times F.
Okay.
Good? Which is equal to negative L mg sine of theta. Nothing weird there. So that's calculating the torque produced by this force. We know that the net torque on the system is always equal to its moment of inertia times alpha.
Yes.
Where alpha is the second derivative of theta with respect to time.
Okay.
Right? Same way that acceleration is the second derivative of position with respect to time. Okay, so combining these two together, since torque is equal to this and torque is equal to this, then this is equal to this, right?
Okay.
So that's why I'm writing here. The torque produced by the force is equal to, what is the moment of inertia? It's mass times its distance from our pivot point squared. ml squared.
And then what are you solving for?
Times alpha. We're just creating an equation.
Okay.
So, we have this equation here. Now notice we can cancel out m and l on both sides, right?
Yes.
And remember that if theta is much smaller than 1, then sine of theta is approximately theta.
Yeah, I remember that.
So we replace sine of theta with theta. This L and M cancel out with an L and M over here. So what do we have over here? We have the negative g theta is equal to 1L alpha. Like that, right?
Yes.
Now I'm going to move this to the other side so that this whole expression is equal to 0. So I have g times theta plus L times alpha is equal to 0.
Okay, I see it.
Now this was our simple harmonic equation. If you have a constant times a position function plus a constant times the second derivative of your position function with respect to time equal to 0, you have simple harmonic motion. The equation theta that satisfies this expression is theta equal to a cosine omega t plus p.
What? Can we go over that expression again? Like why it's equal to that?
Why it's equal?
Why is theta equal to a times cosine of that?
It's a solution. Okay, so we came up with this equation right here. Equations like this we called simple harmonic equations. The way that we first came up with it is you saw something like k times x is equal to, I can't remember, or k times x plus, what was the other constant? I think it was mass. Times m times a is equal to 0 was the first way it came out.
N times a, yeah, you got it.
So, or in other words, k times x plus m times the second derivative of x with respect to t is equal to 0. So I know that this has to be true. Whatever x is has to satisfy this equation.
Yes.
Now notice, here's x, here's its second derivative. Whatever x is, k times x plus m times its second derivative has to equal 0.
Okay.
What is the solution to this equation? It's x equal to, it's a cosine function like this. This is what satisfies that equation. Something of this form. So
if you
things of
plug in,
this form have to satisfy this expression.
so if you plug in x, then all that is equal to 0.
If I were to plug this in for x and calculate all this, then it would come out 0.
Okay.
And that was the very first thing we showed with springs last time.
Yes.
Because we derived, because we manually calculated in the case of the spring what the acceleration would be. Right? We took the derivative of this, we took its second derivative.
Yeah, we did.
Alright. So, yeah, we came up with any equation like this. If you know that an equation like this has to be satisfied, theta has to satisfy this expression, theta has to be of this form.
Okay, I see it now.
Now, it has to be of this form where the omega here is the square root of this constant over this constant.
It
So in
is.
our case, omega, in our case right here, has to be the square root of k over n.
Oh, I see it.
From this expression right here are two constants for g and l. So in this case, omega is equal to the square root of g over l.
Okay.
This was for a pendulum. This is your angular frequency. What does this tell us? This tells us if you increase the length of your pendulum, it takes it longer to swing back and forth. You slow down its angular frequency. If you increase gravity, it speeds up your pendulum. It increases your angular frequency.
Yes.
That's physically what this is telling us. So here's what our omega is. And I know that theta, whatever it is, it has to look something like this. It has to be some constant cosine omega t plus phi, where that omega is equal to this constant. You with me so far?
Yeah.
Now, notice I can take the derivative now of theta.
Which is just omega, right?
There's the gotcha. So notice now, just take the derivative really quick. So the derivative of theta with respect to time is equal to negative omega a sine omega t plus phi.
Isn't
Right?
that velocity?
No, velocity is dx dt. This is angular speed.
I mean, isn't that just omega?
This is how we've been using omega in the past. Omega has been shorthand for this expression.
Okay.
That is not the same thing as this.
So
This right here is a constant. This right here is not a constant. That very much changes with time.
yeah, it does.
It's all over the place.
So why are we using omega for two different things?
Because we use the same variables repeatedly. And you just have to get used to it.
So it's like
And
how
because
we've
they're
been
similar.
using it for G?
I don't know. Sure. I don't know the other way we use G.
I'm saying G is just a standard for a constant depending on what you're talking about.
When we're talking about angular frequency, it's just a constant.
Yeah.
Angular frequency has always just been a constant. Angular speed is something completely different. An angular speed doesn't always show up in our problems. When you had a spring moving back and forth, there was no angular speed. This is a problem where we have a pendulum actually marking out some angle theta. Now there's an angular speed. So a spring, a mass on a spring moving back and forth, there's no angular speed. There is an angular frequency. It has some frequency, and you can talk about how fast its frequency is. But it's not tracing out some angle. This is actually now tracing out some angle. And so it has an angular speed, a speed at which it traces out that angle. And it's all over the place. Naturally, this ball is swinging fastest down here, and so that's when its angular speed is highest. And the ball basically stops when it swings up this way. And that's when its angular speed is lowest.
Okay.
So angular speed all over the place in this example with our pendulum. Its angular frequency is a constant.
Okay.
So here's our definition for angular frequency. Notice that a pendulum swinging back and forth that has a frequency, right?
Yes.
What's our definition of angular frequency? It's 2 pi times the frequency. In other words, if frequency is telling me, frequency is how many revolutions you have per second, right?
Revolutions?
Yes.
How many cycles you have per second, sorry. It's not necessarily a revolution. How many cycles you have per second,
Okay.
right? So if my spring moves back and forth twice in a second, then we say it has a frequency of 2 hertz.
Isn't this also equal to 2 pi over your period?
Yeah, but
Okay.
try to make this intuition quick.
Mean like 2 hertz?
2 hertz means you complete 2 cycles in 1 second.
2 cycle mean it just gets to one side.
No.
That's 1 second.
If I talk about a spring, if I talk about a mass on a spring, and I push it, so it goes out and comes back, that was 1 cycle. And then it goes out and comes back, that was 2 cycles.
Okay.
So a cycle is, it has to get back to where it started.
Yeah.
So frequency is how many cycles per second, right? So if frequency is full cycles per second, and we break a cycle up into 2 pi radians, then omega is radians per second.
When you're doing
If you want to think about it that way.
when you do the units for the hertz, look at it like s to the power of -1. Is that hertz?
Hertz is 1 over seconds.
So s to the power of
Yes. It's cycles per second. The second's in the denominator.
-1. Yeah.
And so if you want to convert from complete cycles, if there's 2 pi radians in 1 cycle, you want to convert from cycles to radians, then you multiply by 2 pi, right? If I want to convert from miles to feet, I multiply by 5,280.
Yes.
If I want to convert from cycles to radians, I times by 2 pi.
Okay.
So F is your frequency, multiplied by 2 pi, that gives us what we call our angular frequency.
Okay.
That's the best I can do to help your intuition with this. So using omega in 2 very different ways. I think for the next 2 chapters, we'll exclusively use omega in this sense. And we'll never use it to stand for the derivative of theta with respect to time.
Okay.
In chapters 15 and 16?
Correct. Probably for the rest of the book that we cover. All right. So I think we got that confusion cleared up. And hopefully that was a good bring you back to what we were talking about problem. Good recap for last time. Yeah?
Yep.
Okay. Now, thought we'd be able to get away without talking about partial derivatives. Turns out that's just There's no way to do this next chapter without talking about partial derivatives, so we're just going to do partial derivatives really quick. And just give you a basic idea of partial derivatives. And when are partial derivatives so useful and why do we have to use them? They're useful when we have a function that is what we call a multivariable function. A function that depends on more than one variable. So y equals xt, or y is a function of x and t, so it's equal to x times t. But now neither of these are constants. These are both considered variables.
Yes.
And so x changes with t and t changes with x.
Okay.
So if we think about y is supposed to give you your y position, and we say your y position is a function of your x position in time, then maybe this is what gives you your y position. Here's some function that gives you your y position at some x position in time. But this is also saying that since x and t are both variables, then your x position also changes with time. Or your time changes with x position. If your x position's at 10, that's at a different time than if your x position's at 5. That's a different time.
Why is this useful?
Well, it's just commonly the case that when we need to talk about something's y position, we need to know both its x position and what time we're talking about. If I were to create a function that were the height of the surface of the ocean at different points along some gap, so say we're looking at something like, I don't know, Lake Michigan. Well, maybe we'll even just say the whole ocean. So first off, since there's more mass of the Earth here and here, sea level actually goes like this. And then it rises some close to the coast just due to gravitational pull. And so sea level's a little bit higher here, right?
Okay. It's higher at...
Close to the coast, because there's more mass there, and so there's more gravity.
Gotcha.
So it pulls the water that way some. So the middle of the ocean, sea level's a little bit lower.
Okay.
Okay, so imagine I'm coming up with some function that gives me the height of the ocean at any x position. Here's my x, right?
Yeah.
But let's also say, you also know that the moon creates tides, right?
Yes.
So at some times, if the moon's in the sky, that also raises the sea level. Versus if the moon's not in the sky, if it's later, then that lowers the sea level.
Okay.
So if I want to talk about the height of the sea at a specific point, right there, I need to know both x, what x coordinate are you asking me to find it at, and what time are we talking about. Both those affect the sea level.
Gotcha.
So if we were to create a function for the height of the ocean, it now depends on two variables, x and t. Where we're talking about and when we're talking about. There's some random example.
Yeah.
So some height, which depends on both x and t, where x and t are both variables. Make sense? Now, we already know how to calculate derivatives of functions like this. We've already actually calculated derivatives of functions like this, where you have two variables in there. So if I know that x and t are both variables, and I want to calculate the derivative of this function with respect to x, then we use a product rule. It's the derivative of the first with respect to x multiplied by second, plus the derivative of the second with respect to x multiplied by the first. So the derivative of x with respect to x, that's just 1. So the derivative of the first multiplied by the second, plus the derivative of the second, that's going to be the derivative of t with respect to x, whatever that is, we don't know, times the first. Right?
Yeah.
Straightforward how we've been doing derivatives this whole time. I could also take the derivative of this function with respect to t, rather than taking it with respect to x. So dy dt, that would be the derivative of the first, multiplied by second, plus the derivative of the second, multiplied by the first.
Okay.
So that's good old-fashioned just calculating derivatives. Now we have a notion of what we call a partial derivative. And a partial derivative is when we calculate the derivative and we treat the other variables as being constant. So if I calculate a partial derivative with respect to x, if I want to calculate the partial derivative of y with respect to x, that means pretend that x is the only variable here. Pretend that t stays constant. Another way to say it is, what would the derivative of this function be if t were constant?
It would just be x, right?
What's the derivative of y with respect to x if t is a constant?
Just t.
Just t.
Oh, just t.
Just t. Similarly, what's the derivative of y with respect to t if x is a constant?
And that would just be x.
Then that would just be x. So that's the difference between calculating a partial derivative and full derivative.
Okay.
And so partial derivatives are useful. It's the derivative if, over here, we're saying this is the derivative if t were to, or if x were to stay constant. Here we're saying this is the derivative if t were to stay constant.
Gotcha.
Right?
Yeah.
Okay. And we'll see how that shows up. All right. So now, ready to start the material for this chapter. And the first thing this chapter talks about are two different types of waves. Really wish I had something to wave. But
Okay.
think back, you ever like played with a hose with someone and you would like send waves back and forth to each other?
Yeah.
Okay, wonderful. So you already have some basic intuitions for things. First off, when you flip your hose up and down and set the wave down, you notice first off the wave obviously moves down the hose, right?
Mm-hmm.
So waves travel, they carry energy with them. Notice what's actually moving in the wave. When you take a hose and you wiggle it up and down, the actual pieces of the hose, they just move up and down. They don't move forward or backwards, they just move up and down. And yet the wave moves down the hose. Right?
Yeah. Okay.
So if you were holding the hose over here, and you wiggled it up and down really hard, and now you're holding it straight again, then that would somewhere have produced a wave. This wave is traveling down the hose, and Jeremy's down here at the other end, and he's about to get whacked by the wave, right?
Yeah.
The hose itself just moved up and down. The hose, that's the best way to say it. So the actual physical atoms of the hose, they just move up and down, and yet the wave travels this way.
Doesn't the wave slowly start to dwindle though?
That's due to properties of, if this were a completely frictionless hose, no internal energy is lost, nothing's ever being heated up, the wave will be perfectly preserved all the way down.
Okay.
So we're going to assume ideal scenarios where it doesn't slowly fade out.
Wouldn't the same energy you put into the wave come out at the other end then?
Right,
Okay.
yes. So waves transport energy from one side to another, but there's no transportation of mass. The mass ultimately just moves up and down and ends up back where it started.
Yeah.
It's just the energy being sent down the hose. Okay, and so this is called a transverse wave. It's called a transverse wave because the direction of motion is transverse to the direction the wave moves. Basically perpendicular to. That's what transverse means.
It's perpendicular to what?
The direction the wave moves. The wave moves this way, yet when you move the hose, you move it this way.
Oh, I
The
see.
wave goes that way from you moving the hose this way.
So the position goes up and down, but the energy is perpendicular.
The wave is perpendicular to the direction of motion,
Okay.
which is called a transverse wave. Does that make good sense?
Yes.
Okay. Now another type of wave that we're going to be talking a lot about is called a longitudinal wave. A longitudinal wave is a wave where the displacement and the wave moved in the same direction. And the best example I can give you for longitudinal waves is thinking about sound. How is it that you actually hear me? What's physically going on there? You might have known something like, there's no sound in outer space. Why is there no sound in outer space?
There isn't any sound in outer space.
Okay, you might not know that.
Yeah.
No one can hear you scream in space, I think is a common expression. No?
Not really.
All right. If it's not, it's not. Let's just think about what sound physically is. Speakers. You have speakers in your car or whatever. Loudspeakers. You ever listen to loud music?
Yeah.
You ever stick your hand in front of a speaker while it's playing?
Yeah.
And what did you feel? You can feel the air pushing against you, right?
Yes.
Or if you stick you might think you're just breathing, but it's also from you talking. You can actually feel the air moving from you talking. And so, sound is just vibrations in the atmosphere. If you get rid of the atmosphere, there's no sound, because there's nothing to vibrate. The same way that I can't send a wave to you without a hose, I keep trying, nothing's getting to you. We need the medium, the hose, to travel through if I was going to send that wave. Similarly, we need the medium, the air, if I'm going to send sound waves to you. Something needs to wave. So
Okay.
what's physically happening is I push on an air molecule right here, which pushes on this one, which pushes on this one, this one, this one, this one, creating a huge chain reaction all the way into your ear.
And that's in a wave movement?
We'll see how it's waving. We'll see what we mean by a wave, by sound waves.
Okay.
But I just want you to see physically what's going on for a second. It's a chain reaction of atoms smashing into each other, going all the way out, and eventually whacking atoms inside your ears, creating vibrations in your ears that makes you ultimately hear me. That's how a microphone works. A microphone has basically a little magnet inside of it, and as the air pushes on that magnet, it jiggles the magnet up and down. That converts it to an electric current. We reproduce that electric current to move some magnet somewhere else, which is a speaker, and creating sound again.
Dang,
That's like the way stupid oversimplified way of how
a microphone works?
a microphone and projecting your voice works. That's what's ultimately happening. We need this medium waving. So let me actually try to draw out what's going on now with sound to help get your intuition down, and then so that you can see what we actually model when we say it's waving. So here's a bunch of air molecules in a room all lined up, right?
Yes.
Now I start talking, which is equivalent to I'm just going to keep pushing the air molecule closest to me. Here's me, you're over here at this side waiting for the sound to get to you. My talking is essentially the same as I'm going to keep pushing this air molecule anytime it comes close enough to me. This little atom here.
Okay.
Right? So I start talking, which means I push that atom. And so after some time, that atom moves forward, right?
Yes.
So from here to here, this is a change of, I don't know, a split second. A split second from here to here as the atom moves forward. And as the atom moves forward, it's going to collide with this atom, right?
Mm-hmm.
So these two collide. As these two collide, this atom gets sent straight back at me, and this atom gets sent forward.
Is that why you can hear yourself before the other person can hear you?
Kind of. That's just because you're closer to where the sound's coming from. But so these two atoms collide now, and now they're going to bounce apart, right? So in the next split second, this one bounces back this way, and this one bounces forward.
Mm-hmm.
Now it's close enough to me that I can hit it again. So I'm going to whack that one again.
Okay.
So I whack that one again, so it's going to move forward. This one collides with this one, so it comes backwards. So these two end up right there, and they're going to collide again. This one got whacked, so now it's going to move forward and hit into this one.
Okay.
See that?
Mm-hmm.
And then once again, in the next one, this is going to bounce back to me, that one's going to bounce forward, that one's going to bounce back, that one's going to bounce forward, and now it's going to hit this one and start it oscillating. So notice what's happening with, pick one of these random atoms, let's look at this one. It bounces out here, then it bounces back, then it bounces out here, then it bounces back, and so it's moving back and forth like this.
In a wave-like pattern?
In a wave-like pattern.
Okay.
So it's jiggling back and forth like this, just like a spring on a mass on a spring,
Okay.
bumping into its neighbors over and over and over again. And notice the wave, the sound wave, is traveling this way, which is the same way that it's jiggling. The air molecules are jiggling this way, and the sound's going that way. So they're jiggling in the direction that the wave's traveling.
Okay.
That makes sense?
Yeah.
So is a spring longitudinal wave?
It's not a wave, but you could create a system of springs that did produce a wave, and then it would be a longitudinal wave.
Why is it a wave?
It's just the one thing by itself. I mean, we can model oscillating motion as a wave, but it's not really transporting energy anywhere. Now, I could get a bunch of springs on masses and make them all collide into each other to send waving patterns all the way down, because that's ultimately what this is acting like, right? A bunch of masses on springs.
Yeah.
You can model this with a bunch of masses on spring, and now we're sending a wave, transporting energy from point A to point B. So that's ultimately what a wave is doing. And being a little bit ambiguous, probably should say like a physical wave versus when we model something with a wave. So a physical wave is transporting energy. Anyways, so notice that there's two ways that we could say that we can model this wave. We can model one of these things jiggling, its Y position changing. So we can model its Y position changing, and that would produce a wave like that, right?
Y position doesn't change.
Sorry, its X position changing as it bounces back and forth, right?
Yeah.
So that's one way we can model it as a wave.
Okay.
Another way we can model it as a wave, if we want to think about the whole thing, is notice now what happens here. So before, here, the pressure everywhere in the room is the same, right?
Yes.
Now notice, once these things get in motion, we've got low pressure here, high pressure here, low pressure here, high pressure here. And so we can also model it as pressure versus position as a wave. And here it's high pressure, then low, then high, then low, then high, then low.
Okay.
And that's another way that you see sound waves. And that's typically what is being expressed when you see like cartoonish versions of waves. When you see like someone has some sort of comic and they have the person talking and they draw out waves like that.
Yeah.
That's high pressure, low pressure, high pressure, low pressure, high pressure. Here's where the atoms are clumped together. Here's where they're spread apart. Clumped together, spread apart, clumped together, etc.
Okay.
So that's two different ways that we can model sound. We can actually model it as an air molecule jiggling up and down, or we can model it as high pressure, low pressure, high pressure, low pressure. And they're both going to be sinusoidal waves. Waves that can be modeled with cosine functions, sine functions.
So why do you care to model them either other way?
Whatever's useful. Depends on what you care about.
Okay.
Okay, some terminology now about waves. So here's some wave being drawn out. We call the high points on the wave the crest of the wave. We call the low points on the wave the trough of the wave. Here's a trough, crest. Pretty straightforward.
Yep.
Yeah.
However much it varies from the center, this distance we call its amplitude. We've already talked about that one.
From the center?
Yeah, however much the wave goes up and down, back and forth.
Okay.
How does
This
that work?
distance right here is its amplitude. Huh?
How does that work on longitude? Because it doesn't go up and down.
We can model this as its x-coordinate, and this with time. And so the x-coordinate of this with respect to time, it's going back and forth, back and forth, back and forth.
Okay.
So it doesn't necessarily have to be up and down motion. It doesn't really matter if it's up and down or side to side. That just means, is this going to be x or is this going to be a y? You can call it whatever you want. But we could have also done something like pressure at a certain time. Or we could have done pressure at a certain displacement.
Amplitude would be like radius, not diameter.
Amplitude is like radius, not diameter. It's this distance. It's not the distance from the highest crest. It's not the distance from crest to trough. It's half that distance.
Do we have a name for that distance though?
Yeah, twice the amplitude. Okay, so that's the amplitude. And then finally we have wavelength. Wavelength is the distance from the peak here to the peak here.
And it's that weird symbol?
Lambda. Yep, lambda. Like a kind of like an upside down line. Is that the first time we've seen lambda?
That is
Okay. Yep, lambda. So lambda is typically used for wavelength. It's the distance between, it's the distance one cycle of a wave takes.
What else is lambda usually used for?
I don't know if I've ever seen it used, I mean I probably have, but I can't think of any other common use case for it other than wavelength. Every time I see lambda, I instantly think wavelength.
Yeah, I've heard about it. I did read a paper on it. That was like antimatter, Einstein's theories. I'm trying to remember if that was what they used or not.
Very common that it's used for wavelengths. So yeah, I can't think of anything else that's typically used for off the top of my head. Okay, so now imagine that, so you and Jeremy, once again, you guys are holding the hose, sending waves to each other. But rather than you just sending one pulse, you're going to keep wiggling the hose up and down, up and down, up and down. And so you're going to be sending a whole sequence of waves like this down to them, right?
And I assume, yeah, that it's consistent. I'm not like going super fast and going super slow.
So you start sending some certain frequency of waves down to them. These are all meant to look the exact same. Don't get confused by the fact one's bigger, one's smaller. So this right here is called our wavelength, right?
Yes.
But these are traveling with time. These are going to be moving this way with time, right?
Mm-hmm.
So how do we calculate the velocity of this wave? What's the velocity of the wave? Let's see, where do I have that written? Velocity here. So how can we calculate the velocity?
How does velocity work?
How fast is this wave traveling down?
How do you measure that? It matters.
Huh?
How do you measure that?
That's what we're going to say. How do we measure it?
Okay.
So, the velocity of the wave, how do we get velocity? It's displacement over time.
Displacement, yeah.
So, the time it takes for this wave, so this right here, this point on this wave, the time that it takes for this wave to travel to this point right here is what we mean by one period. That's time t. Time it takes for this wave to get to here.
Back to its position. Back to where it started, right?
One full wavelength
Okay.
is what we mean by the period.
Would a wavelength and the period be the same thing then?
No. A wavelength is a length, a period is a time.
Oh, so it's just the x position and the time function.
I don't want you to get too tied into x position, because we're going to be plotting these things and we're going to be replacing, are we plotting pressure with x? Are we plotting pressure with time? Are we plotting y with time, y with x? We're going to change those back and forth. And what wavelength and period mean is going to depend on what this is
Okay.
for the wave that we draw. But when we're talking about a physical wave is always going some distance, right?
Mm-hmm.
And we can always represent that. And so this is what we mean when we talk about a physical wave. Only physical waves have velocities. If I just draw something on a piece of paper, some mathematical model, it doesn't necessarily have a velocity.
So the longitudinal doesn't have velocity?
Now, both these do. These are physical waves. When I say a physical wave, I mean a wave that exists in this universe.
Okay.
You can touch it, smell it, taste it. It's a physical thing. I can whack you with it.
Yeah.
Then we also use waves when we're just talking about a model of a wave, a mathematical object. When I just write the cosine function, it's a wave. But that's not a physical wave necessarily.
Oh, I see.
It's just a mathematical object. It's just a cosine function.
Okay.
It still has crests and troughs, and we can still talk about its wavelength, right?
Yeah.
But maybe now period doesn't make any sense to talk about because it's not changing with time. It's just sitting there. It doesn't experience time. It's just a mathematical object. So I'll try to be clear when I'm saying wave versus physical wave. Only physical waves have velocities,
Yes.
right? It doesn't make sense for me to talk about the velocity of the cosine function. Makes no sense.
Okay.
The velocity of a sound wave, that makes perfect sense. You wiggling a hose up and down and sending waves down to Jeremy, talking about velocity there, now it makes sense.
How do you make a sound wave go faster or slower?
You don't. Sound travels at a constant rate, which is 344 meters per second. All you can do is change the
it does have a
amplitude.
velocity, but it's the same all around?
It has a velocity, and it's roughly the same all around. Some things affect it, like pressure affects how fast sound travels.
Okay.
How much mass is in it. For example, our air that we breathe in, the atoms are way more gigantic than helium. Helium is the second smallest atom. Hydrogen is the smallest in helium. Helium is teeny compared to what we're breathing in. And so there's not near as much mass.
Okay.
Well, that's going to change frequency. I think your sound, it can't be the same. Now I'm not positive. Does your voice travel faster in helium? I think it does.
I would assume so. It makes sense.
We'll derive some equations for that. That's going to be next week. We'll talk about helium next week, I'm sure. Not next week, next class. I'm sure that will come up. Anyways, let's stay on topic for a second here. Velocity of a physical wave now. So now you're sending a physical wave down to Jeremy. And that wave has an actual speed. So the speed of that wave, the velocity of that wave, is equal to the distance we go divided by the time it takes to go that distance. So if period is the time that it takes for one wave to get to where, for one crest to get to where the next crest is, for this crest to get to this crest.
Okay.
If that's period, that's time, then the distance is wavelength, and so our velocity is wavelength over time. That's the speed of this wave. Time, or in this case period. Period is a specific time. Period is the time it takes this crest to get to where this crest is.
Yeah.
Yeah.
And the distance it travels is this distance. So velocity is this distance over this time.
Yeah.
Okay, so that is our velocity for physical waves. Our velocity of physical waves is their wavelength over their time.
Okay.
Good?
Yeah.
Now, we also know that period is the inverse of frequency,
Okay.
right?
Mm-hmm.
If your period is 2 seconds, it takes you 2 seconds to get back where you started, then your frequency is 1/2. You're completing 1/2 a cycle per second.
Yeah.
If your period is 1/2 a second, it takes you 1/2 a second to get back where you started, your frequency is 2. You're completing 2 periods per second. 2 cycles per second, right?
Yes.
Okay, so velocity is wavelength over period, or it's frequency times wavelength. Same thing.
So omega over there is 2 pi times frequency, or 2 pi over period. How are those related?
We'll leave that off for a second. We'll come up with models for it.
Okay.
We'll come up with an equation to model a wave yet. We don't even have that yet. So far, we're just talking about velocity. So if you know the frequency and the wavelength, you can calculate the velocity.
Okay.
Or if you know the velocity and the frequency, you can calculate the wavelength. Or if you know the velocity and the wavelength, you can calculate the frequency, whatever. Okay, so now our first example problem. Example problem, we know the speed of sound is 344 meters per second.
Okay.
And then let's say that someone's talking to you, and I don't know if 262 hertz is at a high pitch or a low pitch.
I think it's low.
Think it's low? We'll call it low. So someone's speaking to you in a very low pitch, and we measure the pitch that they're speaking to you with, and it's 262 hertz. What is the wavelength, then, of the sound wave that they're sending at you? That's what we're going to find.
That's 0.44 divided by 262.
Yeah, so he just really said, okay, wavelength is just the same thing as velocity divided by frequency. And then so he said, there's our velocity, there's our frequency, divide it out and you get your wavelength.
Yeah, that's straightforward.
Straightforward.
Okay.
How do you get back there?
Get my calculator. Well, we don't really care what it is for that. So we do 344 divided by 262, and that has a wavelength of 1.31 meters.
Gotcha.
That's big wavelength.
That is a big wavelength. Okay. So got that. Now the mathematical description of a wave. All right.
Fun.
Oh boy. The part I was dreading. I think the example of most waves can be modeled almost identically. So I think the example of you lifting up a hose and sending down a wave is the one that I'm going to think about to try and help make this concept make the most sense.
Okay.
Modeling the wave. So, physical picture, we'll do physical picture with people in it to remind us that it's a physical picture. Physical picture, you're taking this hose and you're wiggling it up and down like that, right?
Yeah.
Now, notice that when we take a snapshot, if we take a picture of you just in time, then the wave is going to look something like this. So this is like a picture. Here we took a picture of you at time t equal to some specific time t1. That's a picture of the scenario. Right? So looking at the whole hose at one instant of time. There it is. Another way that we can model this is rather than looking at the whole hose at one instant of time, I'm going to track one piece of the hose over all time.
Oh, I see.
So instead, I'm going to focus now instead on this piece of the hose right here. So that piece of the hose, it starts out right here, and then it goes up and then down, and then up and then down, and then up and then down, and then up and then down.
Yes.
So right here, what were we plotting? What were our coordinate systems? This was a piece of the hose. We were looking at its height with respect to time, as time changed.
Yes.
Up here, what's our coordinate system? This is just x and this is just y.
Okay, I
So
see.
this was showing the height at a bunch of different positions. This was showing the height of a single piece of the hose at a bunch of different times.
Okay.
It's the same frequency. Right?
Yes. But we're going to capture these all in one go. So what we want now is an equation. We are looking for our equation, hint at where we started. We want an equation, y of t, or y of x of t. We want to come up with the equation that gives us a height at any time x, or at any point x, and at any time t.
Oh, I see what's going on.
Right? Because your height changes with x, and your height changes with time.
Yeah.
Like. the
And so
hose
whatever
itself.
our function is, perfect. Whatever our function is, it needs to capture both these things. Okay, so we're going to start by in coming up with what this function has to look like. We're going to go back. You're waving up a hose. You're waving the hose up and down, up and down. We'll assume that you start with the hose at the top, and you start by swinging down and then up and then down and then up. You with me?
Yeah.
And we're going to model the piece of the hose that's directly in your hand. The first piece of the hose. So in other words, where x is equal to 0.
Okay.
So when I model my function, when I look at my function, y of x, and we're going to start with x equal to 0, and then time is going to vary. And let's draw this out again. Shouldn't have erased these. So one of them could probably be a little bit more precise here now. So one of them is looking at your hose with respect to position. So this was your height of your hose y. This was with position x. And then we can look at some piece of the hose, just looking at a piece of the hose with respect to time. And the piece of the hose that we're talking about is going to start out up here. It's going to start out at the top. It's one in your hand. And then you're going to wiggle up and down. So this is a picture of the hose at some time. This is at t equal to some time t naught. This one down here, we're just going to follow the hose in your hand as time goes forward. So it starts out at the top, and then you bring the hose down, and then you bring it back up, and then you bring it down, etc. Right?
Okay.
So down here, we're looking at just a piece of the hose. This is a picture where x is equal to 0. And this right here is y. So down here, we're looking at a specific point, x equal to 0. This is what it looks like at some specific time. Here's at some specific position. You with me?
I'm with you, but did you get your words mixed up?
I don't know. We're looking at this picture right now for this equation. This equation, we're looking at this picture. X is equal to 0. So we're looking at the piece of the hose in your hand. X is going to stay 0 as you wiggle it up and down. Since you're not moving forward or backwards, you're just wiggling up and down. So X stays 0, and all it's changing is the time. As time changes, the height changes.
Gotcha.
So that's what we're modeling right here.
Okay.
Where x specifically is equal to 0, and then we'll get more general here in a second. Okay, well, if x is equal to 0, as we wiggle that hose up and down, obviously this is creating a cosine function. So it's going to be a times cosine of, and then we're going to have some angular frequency depending on how fast you're doing it that depends on time.
What about feet?
There's no angular offset since you're starting at 0.
Yeah.
You're using angle acceleration?
Angular frequency. Angular frequency. Not angular speed.
Okay.
Same thing we've been using for simple harmonic motion. Same omega. another way we could represent this is equal to A times cosine of 2 pi times the frequency times t. Same thing, because by definition of our omega, when we're talking about angular frequency, it's 2 pi f.
Okay.
Okay, so that is looking at the piece of the hose at x equal to 0. Now what if we want to look at a piece of the hose some distance down the road, what if we wanted to start out at this position x now?
Well, that would be
We'll
the
call
same
that
as
x1.
x equal to 0, right?
Some later position, any x1.
Yeah, but you completed a full period.
That I just happened to draw there.
Oh, okay.
Any random x1 forward.
Gotcha.
It's just, there happens to be the most space right there. So any random position x forward now, because we don't want to just keep our x equal to 0. We want x to also be able to change with time. Or we want to be able to plug in any x we want. So as we choose a different x here now, x1, what is x1? Well, notice first off that x1 is the distance from here to here, right?
Okay. Wouldn't that just be your upside down y minus your x1? That distance?
No. So this happens to be lambda. This x1 could be anywhere. It could have been 10,000 miles down the road.
Oh, I see.
Okay? Just a random x1, random position somewhere. Now, what I'm looking for, I want to know the time now. I want the time t1 that it would take my wave to reach x1. So when does my same starting point get to x1? When is that t1? And that's going to be, what's time? We can calculate it as displacement divided by velocity.
Time is this, okay?
Right?
Yeah.
So I can represent this as, that's going to be x1 over v. And that is when my wave that I started with, the point I initially mapped out right here, that's when that part of the wave would reach here.
Reach to your point, x1.
Reach x1, some other future point. I need room to write equations. Maybe I'll erase this one for now. So if we want to write this equation in general, I don't want to skip right to that. I guess I could, then why did they have me plug it in? So looking at this one for a second. So now for any time, for any x coordinate now, so if we have y at x comma t for any x now, the time that it takes to reach this x, we can calculate from time equal to x over v, for any x that you have here. That's the time that it takes to reach that x.
So you just plug in x over v for t?
Almost. So this is equal to a cosine of, square bracket here, square bracket, of omega times t minus x over v.
What?
So x over v is the time that it takes the wave to reach here.
Yes.
So the wave at time 0 here is the same as the wave at time t1 here. So at time 0, the wave is at its height right here, right?
Yeah.
And now the wave is traveling this way. And at time t1, the wave is now right here.
Yeah, time t1.
So at this position, the wave is at the same height at time t1 that it was at 0 here.
No, because it's for any
At
x.
time 0 here, the wave was at its peak. At time t1 here, the wave is at its peak.
How do you know it's at its peak?
Here's the top of the wave.
You moved it
Yes.
to the left.
As the wave moves forward, this is the top of the wave moving forward. After time t1, the top of the wave has moved to right there. This atom, not that atom, this wave is moving this way. All these waves are moving. Right?
Yeah,
We're looking at just this position.
but it's on the
So at this thing's position, it drops down and then it comes back up. as this wave moves forward.
Yeah. Okay, I see that. Wait,
Why
you don't know that though, because your x could be any part of the wave. It could be the bottom part, right?
Look at x1.
Okay.
It's a coordinate. It's 1 meter out. I'm sitting here, I'm at x equals 0. You're at x equal 1. So I have a rope that I'm jiggling up and down right here.
Mm-hmm.
You are required to look at just this point on the rope. And this point on the rope moves up and down. You're watching it. You are now x1. You're sitting right there watching just that piece of the rope.
And all the rope's doing is
And all that piece of the rope right here at x1 is doing is moving up and down.
Yeah. Okay, that makes sense.
Right? So as this wave moves forward, this wave is going to travel forward, right?
Aren't we taking a snapshot of the wave?
This is a snapshot. Right now we have a snapshot to talk about.
But it's not on the peak at the snapshot.
Right now, x1 is not at its peak.
Yeah.
Let's move x1 to make things super, super clear. We'll pick x1 right here. x1 right here. At time t equals 0, so this is our picture at time t equals 0. Here's our picture of the wave.
Mm-hmm.
Right?
Mm-hmm.
We just started the process. Well, let's not say we just started the process. There's been waves going the whole time. T equals 0 is when your hand's at the top. And now we're going to start stopwatch. We're going to start tracking time.
Okay.
So at t equals 0, there it is. Here's our picture at time t equals 0. Now if we go into the future, a split second now, what's going to happen? x1 is going to go down some,
Yeah. Okay.
because the wave is traveling forward. x1 is going to get lower. We're going to have a slight time into the future. What's it going to look like? Let me grab another marker. We go forward into the future for a second, and now the wave's going to look like this. Right?
Oh. Yeah.
Moving forward into the future some.
Yeah.
So at x0, the wave went down. At x1, the wave is now clear down here.
Okay.
Okay. So now, yeah, this is the part I was worried was super confusing. So now, time t1, is the time it takes for this wave, the height of this wave, the middle of this wave, the crest of this wave, to reach x1. It's the time it takes for this wave to get right here. That's what t1 is,
Okay.
right?
Okay.
So, the height of x1 at time t1 is the same as the height at x0 at time t equals 0. The height here at time t equals 0 is the same as the height here at time equal to t1.
Well, yeah, because you define T1 to be that height.
Exactly. To be that time.
Yeah.
The time that takes the wave to get there.
To get
Yes,
to that height.
that's exactly what t1 is defined to be.
Okay.
Okay, so here was our function at just x equals 0, right?
Yes.
So, well, looking at this one. So our function now, if we were looking at x equals 1, if we plug x equal 1 into that thing, needs to behave the same as this thing. This one at t1 needs to behave, this one at t1 needs to behave the same as this one did at t0.
Yeah, that makes sense.
And that's why we have this minus here. Notice that we are subtracting, this was a substitute for t1. So erase this for a second, forget about this for a second, let's plug t1 into there.
Okay.
t1 is the time it takes when we plug in, if we're looking at x1, so here we're now looking at x1. Here's the height of our function at x1, right? For any time t that you choose. And the height at t1, when you plug in t1, so if I plug in t1 for t, what does this become?
0.
0. So I take cosine of 0, which is
1.
when it's at its max.
Oh.
So when you plug in t1, this whole thing has to spit out a 0, so that cosine spits out 1. It needs to be at its max.
But what if when
So we
it's
have to
not T1?
subtract t1 from t to make so that at t1 we get a 0. So that plugging t1 into this is the same as plugging 0 into this. that's why we subtract the T1.
Okay.
Is that clicking?
What if your T is less than T1?
If my T is less than T1, then we get a different number. It's going to be slightly less. So if you didn't quite wait T1, then if we took our time picture right before T1, then the wave is going to look something like this. It's going to be a little bit less. You need to wait till T1 so it can get exactly there. At T1 is when the wave gets exactly to, so that the height of the wave is at that point.
What's your T?
T is any time. So this is a function in terms of T still. Plug in any time and this has to give you the height. At the point x1 now. Here was the height at x equals 0. Here's the height at x1.
Okay.
You getting it?
I think so.
Okay. So the only difference between the height at x1 and the height at any point x is, well, first off, create our substitution here. T1 now was the same thing as x1 over v, right? You okay with me plugging that back in?
Yeah.
Yeah.
Okay, so now the only difference between doing it at some point x1 and at any point x is erase your subscript. For any point x and for any time t, this will give you the height.
No matter what, on any wave.
Well, on these waves.
What type of waves are these?
Right now we were talking about moving a hose up and down, or moving a string up and down.
So just
Transverse waves. Turns out these are going to be the same for these mechanical waves, but for example, you can't automatically assume photons behave this way.
Oh, but photons is like way down the road.
Sure.
Okay.
I mean, we deal with photons all the time, but however you want to say it.
Didn't you say these are the only two types of waves?
These are the two we'll be most interested in, these two physical waves.
Oh, but
They're not the only types. You could talk about the waves on top of water, and they kind of move in cycles like this. They're kind of like longitudinal and transverse waves. But I don't have a good way to show you that, and so I didn't want to get into it. Because that's hard to see.
The book talked about it though.
But there's the crucial point, the equation that we have right here. This gives you the height of the wave at any time t and at any position x.
What if you know an X but not T?
We are not, all we were trying to do was come up with a height function. That's all we were after so far.
So this is just giving you the Y.
This is just giving us a y.
So you have to know both the X and the T for this to work.
Right. If I'm sitting here and I'm sending you a wave on a hose, and I say, quick, Peter, what's the height? The height of what? The piece of the hose. When? Which piece? You need to know which piece of the hose you're talking about, and you need to know what time you're talking about. Then we can talk about the height. So the height depends on position and it depends on time. It's a multivariable function.
And you have to have both in order to find out the height.
Yes, you need to know both x and t to figure out the height.
That's kind of cool. Okay.
Otherwise the question doesn't make sense.
Do you always have to start out up on this wave for this formula to work?
This formula is choosing, as a matter of convention, to call t equal to 0 when it's at the top.
What if it wasn't?
Rename your t's. It's like you're changing your time axis. When are you starting your stopwatch? You're saying, well, if I start my stopwatch a little bit sooner. Don't. It's the same as shift your x position or your y position. X or y coordinate system.
Would the formula still work?
No, you'd have to take that adjustment into account. You'd have to allow for some sort of phase shift, which is going to make the math get ugly. You need like a plus phi type thing. So we don't want phase shift because this is already ugly enough.
So it's dependent on the frequency and the X and the T. Or is the frequency a constant?
Huh?
Where's the frequency? Yeah, frequency. Is the frequency a constant or is it a variable?
In this case, we're only going to worry about ones where it's constant. I doubt we'll deal with variable ones. where he's sending you the wavelengths and then he speeds up and then slows down and then speeds up. No. So we'll be doing constant frequencies. The frequency comes in right there, the angular frequency. And yeah, we're going to treat those as though they're constant.
Okay.
Okay, so here's our equation so far. Now we've got all that, I need to do a bit of math, so I'm going to erase this and move that equation up. And then start
A
playing
is
with
your
it.
amplitude?
Yes. So y at xt is equal to a times a cosine of omega times t minus x over v. And we'll end up splitting those up. Not sure when he wants to. He has like 4 different ways of writing the same equation, so I'll try to write out each one of those.
Okay.
But there's just the one that I find the most useful, which is one of the ones we'll come up with. Okay, so first thing, just as a matter of convention, doesn't change anything, but so note really quick that cosine of theta is equal to cosine of minus theta. Those are the exact same. If you do minus theta, that flips from talking about the top of the circle to the bottom of the circle, and that doesn't change your x-coordinate, it just flips your y-coordinate.
Oh,
Your x-coordinate at 30 degrees and at minus 30 degrees are the same.
Yes.
So cosine of theta and cosine of minus theta, they're the exact same. So I'm going to put a minus into this thing, or in other words, I'm going to switch the order that those two terms are written. So I'm going to rewrite this as y of xt is equal to a times cosine of omega x over v minus t. Doesn't really change anything, just more conventional to write it that way. Good?
Okay.
So this is one of the ways that the book will give you this equation written. When you get to the end of the chapter, they'll have like 4 different versions of this equation written. Just depending on what you're given, you know which equation to use. Let's see. The other way that they have this equation written is they take that and they replace omega with 2 pi f. And so it's also written as a times cosine of 2 pi f times x over v minus t. So there's another way that they have it written.
Okay.
The other way that they have this written is, let's see, period. So he notes period is the same thing as 1 over f, and he notes, let's see, I think we're going to try and force a wavelength to show up in this one. So, and wavelength is equal to, did we erase our equation? Okay, right here. Wavelength is equal to velocity over frequency. Right?
Yeah.
And so, what he's going to do is, you put my equal sign right here, same equation. I'm going to bring the f inside of this equation first. So this is equal to a times cosine of 2 pi, bring the f in, so we have x times frequency over v minus t times frequency. Right?
Yeah.
That was just moving the f in. Now notice that v over f is wavelength, so f over v is going to be 1 over wavelength.
So just x over wavelength.
X over wavelength, and then f is 1 over period. So this is equal to a cosine 2 pi times x over wavelength minus time over period. So here's not a terrible way to have the equation written out, because notice it's just 2 pi, and then you have your position over your length, and your time over the time it takes for one interval. So the length of one interval, the time of one interval, and then x and t. So not a terribly unintuitive way to remember the equation,
Okay.
but still not the way I like to think about it. Finally, remember from last week we introduced the wave number, k, which was 2 pi over lambda.
We went over that?
We must have introduced lambda last time, you guys just don't remember.
No, I don't remember that sign.
We didn't introduce wavelength, or wave number?
I would remember that.
Yeah, I would have remembered that sign too. Never seen it before.
How did we introduce K last time? We definitely introduced wave number.
Wave number.
That was introduced in chapter 15.
I'm talking about how we introduced K.
K was...
I don't have it written down.
You don't have 1 half KA squared.
Not K as in the... Okay, we didn't go over wave number. All right. Weird, my memory is lying to me. All right, so this K, obviously not spring constant. This is called the wave number. Wave number is the number of waves we have in a single cycle. Take a cycle divided by the wavelength. Tell me wavelengths you can fit in one cycle of it.
What's a cycle again?
2 pi. That's what I'm saying for a cycle. 2 pi divided by the wavelength is your wave number.
Okay. Don't we use K like 3 other times?
Yeah, K is very common for just some constant that comes up.
Don't they have any more Greek letters?
So let's see the substitutions that we are using. So let's see. If I just knew where it was going, I could figure it out from there. Just write down what he has here and then we'll make sense of it. So he says, substituting we get from this, we can rewrite lambda is equal to 2 pi over k, which is obvious, swapping those two.
Yeah.
And then he says, we also have f is omega over 2 pi, which is obvious from our definition of omega over there. Velocity equals wavelength times frequency. Okay. Velocity equals wavelength times frequency. And velocity equals wavelength times frequency. That one we have written right here.
Yeah.
Okay. It's convenient to use a quantity k called the wave number that we have, substituting that, lambda equal that, f equal to that, into here. So we're substituting into this, and we're substituting in lambda and frequency. Okay, so let's see what we get, and then we'll see if we can just figure out where he's going with this. So velocity is equal to lambda, 2 pi over k, times the frequency, omega over 2 pi, which is equal to omega over k, is another way that we can write our velocity.
Okay.
So how does that help us with that equation? That can't be where we're substituting in. We're probably substituting like up here somewhere. So then we can rewrite this as, I'm not sure what it's saying. We'll come back and reference as we need to. I'm just going to distribute this in and start cleaning up and see what we can do. So let's see. We have this is equal to a cosine of, if we bring the 2 pi in to the x, we're going to get 2 pi x over lambda minus 2 pi t, and maybe put that t back up there for frequency, because that looks like something that we have to play with here.
Okay.
Now notice that 2 pi over lambda is exactly equal to k. That's our wave number. And then, yeah, I don't know why he wrote all this other nonsense out. Forget all that. Just put our wave number up here.
Okay.
You just make some massive things sometimes. So 2 pi over lambda. That's all we care about for our wave number. Okay, so we see that here's our wave number here when we put the 2 pi in there, right?
Mm-hmm.
And then 2 pi times f is the same thing as omega. So this is equal to a times cosine of 2 pi over lambda. I'm replacing that with k, so we have k times x. And then we have minus 2 pi times f, 2 pi frequency. That's exactly what omega is. So minus omega times t. And that's the way I remember it.
Yeah, that was a lot less complicated.
Okay, so that gives us our position with respect to x and with respect to t. Graphing, we talked about the difference between x and t. Okay, now when we are following, maybe you make note of this point right here, that portion we call the phase. So the phase of our wave is this internal part, kx minus omega t, and that's telling us what point we are at in the wave. Notice that everything inside of here just gives us our theta. It gives us what we're taking the cosine up.
Yes.
And so if it's 0, then our wave is at its max. If it comes out a multiple of pi halves, then our wave is at 0. If it comes out a multiple pi plus 2 pi, if it comes out so it's basically at the bottom of our circle, then this comes out -1. So this tells us what phase our wave is currently in. Is it up here? Is it down here? Is it somewhere in between? This tells us our current phase.
Okay.
You with me?
How does it tell your phase?
Well, that's what it gives you, the phase. If I give you the k, the x, and the omega and the t, that's telling you what phase the wave is in.
How do you know which phase based on what it gives you?
Phase just meaning, is it at its top? Is it this high? Is it this high? Is it down here? We just refer to everything inside of here as the phase. It's just a name.
But how do you know which one it's in? How do you know if it's in the top versus the bottom?
Well, if I give you these numbers, if it comes out 0, then the wave's at the top. Or if it comes out 2 pi, then the wave's at the top. Or if it comes out 4 pi, the wave's at the top.
And if it comes out -1, is that the bottom?
And if it comes out negative pi, when you calculate the cosine of it, notice cosine is always a number between -1 and 1.
Yeah.
So this whole thing just spits out numbers between -1 and 1. If it spits out 1, we're at the top of the wave. If it spits out -1, we're at the bottom of the wave. If it spits out 0, we're in the middle of the wave. And then depending on what it spits out tells us where we are in the wave.
Okay.
So this stuff inside our cosine function we call the phase. And it tells us what phase the wave is in.
Okay.
Because if the stuff inside of here comes out 2 pi, then when we take the cosine of 2 pi, we get 1. That tells us our wave is at the top.
Yeah.
Okay, so that's what we mean by the phase. Now, intuitively, if I were to ask you to calculate the speed of a wave, so we go back to our hose and I send a wave down the hose, how do you track the speed of the wave? What do you even mean by how fast is a wave going? What you do is, if I'm sitting here waving something, so it's sending waves over and over again, and I tell you to run along at the same speed as my wave, what would you intuitively do? You'd pick some point on the wave, you'd pick some portion that's in a specific phase, so maybe you'd pick one that's at the bottom, and you'd keep up with that portion of the wave that's at the bottom, right? In other words, you follow a part of the wave that's in a constant phase.
Gotcha.
If you're keeping up with the wave. So if you're traveling at the same speed of the wave, you're following a part of the wave where the phase is constant. If the phase is changing, you're not keeping up with the wave.
Gotcha.
If you're traveling exactly parallel with the wave, then the wave is going to be constant relative to you at your position, right?
Mm-hmm.
So when you are traveling at the speed of the wave, then the phase is a constant. So at V, then kx minus omega t is equal to some constant.
At velocity?
At V, where V is the speed of the wave. if you're traveling next to the wave at the speed of the wave, then at your position, the wave is constant. The phase isn't changing. That's what it means for you to be standing right next, traveling at the same speed of the wave.
Okay.
I
Makes
mean,
sense. Yeah.
yeah, I think you guys are getting it. Here's some portion of a wave, right? And it's waving up and down, sending through it, so wave is traveling forward.
Mm-hmm.
If I'm traveling at the same speed of the wave, I pick some portion of the wave, pick some phase of the wave, like right here, and I stay up with this part of the wave. So as the wave is traveling, relative to me, if I just look over to it, the wave isn't traveling. The wave is staying in phase.
Okay.
The part of the wave that I'm traveling with doesn't change. The phase stays constant, right?
Yeah.
That's what we mean. So at v, at the speed of the wave, your phase is a constant. So now, really quick, take the derivative of both sides with respect to time, and what do we get?
With respect to time,
Mm-hmm. So over here, we
wouldn't
have,
that first part equal to 0 then?
I assume that's what he's doing here. So this right here, when we take the derivative with respect to time of this, it's going to be k times dx dt, whatever that is.
Isn't that velocity?
And that's velocity, wonderful. Minus omega, what's the derivative of t with respect to t?
So,
1.
so
The derivative of t with respect to t, 1. Okay, is equal to, what's the derivative of a constant with respect to t?
just a constant.
0.
0. The derivative of a constant is 0.
Oh, if it's a constant times t, then I'll just, okay, I see.
We're taking turns with getting the derivative.
Yeah.
Anyways, now solve for dx dt, and what do we get? We get that dx dt is equal to omega over k, or in other words, v is equal to omega over k.
Oh, which we already showed.
And so, there's another way that we can get the speed of the wave. The speed of the wave is omega over k. Now, we already had the speed of the wave is equal to frequency times wavelength, right?
Mm-hmm.
So, let's show that we already knew this. This was just another way to see it and make intuitive sense. Well, we already know that velocity was frequency times wavelength. Now, from our definition of k up here, I could rewrite wavelength as 2 pi over k. So this is frequency times 2 pi all over k, right?
Did you know what frequency is?
And then frequency times 2 pi is omega.
Yeah.
So omega over k. So we already knew that, but another intuitive way to see it.
Isn't omega times your radius equal to angular speed?
There is no radius.
No, I'm saying, I'm making connections to our previous lessons. I'm saying, isn't omega equal to velocity times your radius?
That's angular.
No. That was angular. That was our old omega. That was a derivative of theta with
Yeah,
respect
I'm
to
not
time.
saying that that happens to be the case with this. I'm just saying,
Completely different omega. This is our constant omega.
yeah, I'm saying what's going on is before you were timesing it by the radius, now you're dividing it by your constant k.
This omega has nothing to do with that other omega. Pure coincidence. We just repeated a variable. That other omega is dead and gone. It's never coming back. That other omega was d theta dt. D theta dt, if we multiply it by r, gives us d theta times r dt. D theta times r is dx. Dx dt is velocity.
Okay.
That came from d theta dt. This has nothing to do with that. This is a constant. And so
Omega's
our
a
velocity, the speed of our wave, is a constant.
Oh, I see. Okay.
It's not something changing with time. Okay. Going to be lots of confusion about that because they're very similar, and they're both radians per second. Sure, why not? Let's do a mouthful of an example now. Yeah, we'll do it. Okay, so some guy holds one end of a clothesline taut and wiggles it up and down sinusoidally, just creating a sine wave, with frequency 2 Hertz and amplitude 7.5 centimeters. The wave speed of the clothesline is 12 meters per second. At time t equals 0, the other person's end has a maximum positive displacement and is instantaneous at rest. Assume that no wave bounces back. Find amplitude. All right. So start writing down a bunch of things that we know. So we've got someone jiggling the wave up and down. We know that this distance right here is 0.075 meters. We know that the frequency that they're jiggling this was 2.00 hertz is what they gave us for our frequency. And we know that the velocity and the speed of the wave is 12.0 meters per second. That's the velocity that these waves are moving forward with. So we're first supposed to find the amplitude. So what's the amplitude? 0.075 meters.
Okay.
Omega t lambda k. So we're looking for omega t lambda and k. So let's find each of those. Omega is equal to 2 pi times the frequency.
Yeah, so that's pretty straightforward.
Um,
4 pi.
Yeah, we have to use significant figures. So 2 times pi is equal to 12.6 hertz. Or not hertz. 12.6, and that's radians per second. Our period is 1 over our frequency. So if our frequency is 2, then our period is half a second.
Yeah.
Our wavelength is our period times our velocity gives us our wavelength, right?
Or your velocity divided by your frequency.
Or your velocity divided by your frequency, but you're used to thinking about distance is speed times time.
Yeah.
So just whatever helps it click in your head rather than having to memorize equations is the way I'm trying to get you to think about it.
Oh, I see.
So our wavelength, because you don't have to memorize the relationships between all these things. You want intuition so that you can just think about it. So we got 12 times 0.5, don't know why I'm writing that out. Obviously our wavelength is 6 meters. Now our wave number is 2 pi.
Wait, how'd you get to 6? Oh, yeah, I see.
Our wave number is 2 pi divided by our wavelength, divided by lambda. That was going to be a little over 1. So 2 times pi divided by 6 gives us 1.05 is our wave number. Okay, so we found all those numbers. That was part A. B, write a wave function that describes the wave. So our wave function, y of xt, is equal to our amplitude, 0.075, times the cosine of, we have kx, here's our k, 1.05x minus omega t. Omega is 12.6 t. And there is our position function for this particular wave. Let's see, what else? Write equation for the displacement as a function. Write a wave function describing the wave, okay. Write an equation for the displacement as a function of time of Throckey's end of the clothesline and of a point 3 meters from the end. Okay, so here's our wave function. Now we want a wave function that just describes the height of the wave, or the height of the portion of the rope that's in your hand. This is the height anywhere at any time, right?
Mm-hmm.
So now they want us to come up with an equation that describes the height that's just in the portion of your hand. The portion in your hand is x equal to 0, right?
So it'd just be y depending on your t.
Yeah, so y, where x is equal to 0, t, is just equal to 0.075 times cosine of, that's a 0, so it's just negative 12.6 t. That's the height of the portion that's just in your hand at any time t, right?
Yeah, I see.
And since cosine of negative is the same thing as just cosine of that thing, we can get rid of that negative sign.
Okay.
And then they said, now find the height. Find a function that describes the height of the rope 3 meters away from you. So where x is equal to 3.
Oh, so it's just 3 times omega.
0.075 times cosine of
3.15 x.
3.15 minus 12.6 t. All right. I think that was everything. So now let's check all our answers. Make sure we got all of it right. I'll just read it. You check on the board so I don't lose my place in hard times. Okay, amplitude 0.075 meters, frequency 2 hertz. Omega is 12.6 radians per second. Period is 0.5 seconds. Wavelength is 6 meters. Our wave number is 1.05. Our wave function is A times, they did it the dumb way. Okay. Our wave function is equal to 0.075 times cosine of 1.05x minus 12.6 t. Our height function at x equal to 0 is 0.075 cosine of 12.6 t. They messed up. They put the t outside of the cosine. And then our other height is 0.075. What did they do? Oh, that's what they did. So this 3.15, it came from this, but this was the wave number k. So ultimately, our function that we were plugging into the whole time was y at xt is equal to a times cosine of k times x minus omega t, right?
Yeah.
And the way that we calculated k here, k was equal to our wavelength divided by 2 pi.
Other way around.
Thank you. 2 pi divided by our wavelength. Where our wavelength was 6, right?
Yes.
So k is actually exactly pi. This was a rounding for when you give your answer, right?
Okay.
Which means, no, not exactly pi, sorry.
1/3 pi.
Pi thirds.
Pi thirds, yeah.
So when you, okay, so now down here, when we plugged in x equal to 3, then it would have actually been 0.075 times cosine of instead of, huh?
Just pi, right?
Just pi minus 12.6t. Now we can't leave that as our final answer because we need to round pi to 3 decimal places. When it's all said and done, we need to round to 3 decimal places, right? But using a trig identity, cosine of pi minus your angle is the same thing as negative, just the remaining angle. So this, using trig identities, comes out 0.075 times cosine of 12.6t. Okay, so there's the answer that they give in the book. That's how they got there.
Isn't that the same as x equal to 0? Oh no, I see it now. One's negative, one's positive.
One's negative, one's positive. Okay.
Interesting.
So that's how they came up with that answer. So remember that you don't have to round to 3 significant figures until you're giving your final answer, and it's better not to round until you're ready to give your final answer. Since we rounded early, we didn't notice that we could get rid of that term altogether.
I see.
I don't think I would have noticed that anyways. Which trig identity is that? Like, is that just because you go half a circle with pi?
Cosine of pi minus phi for theta is equal to negative cosine of theta. It's like if you start counting at the other end, well, I don't have a good way to help you visualize it. I guess one thing we could do is cosine of that is the same thing as cosine of theta minus pi. And then when you phase shift by pi in your circle, if you jump ahead pi, then now you just got to your negatives instead of your positives.
Okay.
You're going to be counting negatives now when theta by itself is counting positives, and then positives when the other one's counting negatives. I don't know, whatever makes it quick. You can always just graph it, look at its graph, and then see what giving it a phase shift does. And it just flips all the directions if you have a phase shift to pi. Anyways, there was the example problem. Okay, so now we need to derive our wave equation.
Our wave equation?
Yes, the same way that we had this equation right here was our simple harmonic equation. Anytime this came up, we knew that we were dealing with simple harmonic motion. We're going to do a similar thing, come up with our wave equation, so that anytime this equation comes up, we're dealing with waves.
Yeah.
Okay.
And it's one of your big equations in physics, not necessarily for this class particularly, but generally when you take physics, your first class, which we're doing right now, is often called classical mechanics. Your second class is often called electricity and magnetism. And then your third class is waves. So physics 3 is like completely focused on just the physics of waves, which is where it would be huge. So this is meant as like a intro to prepare you for when you ultimately take physics 3.
I see.
Right?
Yeah.
Right.
Maybe so it's not your first time seeing it. Get our equation back up here. Y of xt is equal to a cosine. We'll use this version of it because it's the easiest to use. Okay. So here we have this equation. Now we're going to take partial derivatives of this equation with respect to x twice, and then we're going to take partial derivatives of this equation with respect to t twice.
Okay.
So it doesn't really matter which way we do it first. We'll start by taking partial derivatives with respect to t. So now the derivative of y, the partial derivative of y with respect to t, is equal to,
What is it equal to?
practice taking your partial derivatives. Huh?
It
You're
would,
just treating t as the constant?
Treat t as though it's the only variable.
Oh.
wouldn't k times x minus w?
It's just a chain of the outside times the inside.
So tell me what to write.
Negative
negative a sine
Of, in the parentheses, kx minus omega t multiplied by
K times x minus
Omega.
w minus omega.
minus omega, yeah.
Just minus omega?
yeah.
That's the derivative of the inside. What's the derivative of this if t's our only variable?
0.
What's the derivative of this?
Just omega.
Negative omega.
Okay.
So this is equal to omega a cosine, not cosine, sine of kx minus omega t, right?
Yeah.
Yes.
And then just now, this also gives us our velocity in the x direction, just to help you get useful thinking about it that way, or our velocity in the y direction. That's how you calculate it. Our acceleration, our next derivative, which is also the acceleration in the y direction, just for reference, not that it matters for the problem that we're doing. We take the derivative again, so the partial derivative of y with respect to t. This time we're doing the second derivative of y with respect to t. Once again, take the derivative of this thing. What do we get? Then we get negative omega squared times a cosine kx minus omega t. What do we know about that?
Has a negative omega squared.
It's the same thing as our sublime line of motion.
It's the same as what we started with,
That too.
Okay.
with just a negative omega squared out here, right?
Yes.
So this is the same thing as negative omega squared times y times our function that we started with, times our position function.
Okay.
Very similar to what we already did. You already see the similarities. We've already basically done this before
Yeah.
a couple times now. Okay, so that was taking the partial derivative with respect to t. Now we're going to take our partial derivative with respect to x. So now I'm going to take the partial derivative of y with respect to x, and what am I going to get?
Well, just the opposite way around. It's just
Tell me what to write.
k times a times sine of kx minus omega t.
Almost. Forget one thing.
Negative.
Negative. Right? The derivative of cosine is negative sine. The reason that this term didn't end up having a negative is because of the negative from the omega cancelled out with it.
Oh, I see.
And this one doesn't have that same negative. Okay, so there's our partial derivative of y with respect to x. Now let's take our second derivative of y, second partial derivative of y with respect to x. And what's that going to be equal to?
Sorry. With respect to x,
Uh-huh.
this time you'd have a k squared times a times cosine of kx minus omega t.
Which is the same thing as what?
K squared times your original function.
Negative k squared times our original function.
Wait, why is it negative? Wait, the negatives cancel out?
There's no more this time.
Where would
It's
the other
just
negative come from?
derivative.
Derivative of sine is just cosine.
Yeah. Oh, I see.
Good?
Yeah.
Okay. So now, I am going to look at the quotient of two terms. Let's see, which one do I want on top? The partial of t on top. So I'm going to look at this term divided by this term. So I'm going to look at the second derivative of y with respect to time divided by the second derivative of y with respect to x. Sorry, my deltas are atrocious. And what does that equal? That's going to equal this over this.
Well, your negatives cancel out.
Perfect. What else cancels out?
Your omega over k is just velocity, and if that's squared, wouldn't that just be velocity squared?
Perfect. So the negatives go out. Omega squared over k squared is just going to give me velocity squared.
And then your other equation goes out.
And then that cancels out. Perfect. And then so, finally, the way that this is typically written is we write this one in terms of this one. So it comes out this way. Little unintuitive with how it's typically written, but that's how it's typically written. Is equal to 1 over v squared times the second derivative of y with respect to, with respect to t squared. Second derivative of y. Just so you know, the way that the book keeps writing these y's, so when you look in the book and you see this equation, just so you don't get confused, I just have a y here. They write y of xt every time, and I find that tedious. So they have that there instead of just y. They have that there instead of just y.
Gotcha.
But that should be the only difference between how I wrote it and how they wrote it. Okay, so there's our wave equation. So if you have some function y of x and t that satisfies this expression, then your function y of x and t is a wave equation. Same way that if you had some position function that satisfied this, you had a simple harmonic, your function was a simple harmonic function. If I have some function y that satisfies this, it's a wave function. If when I take a second partial derivative with respect to x, and I take a second partial derivative with respect to t, and they're related to each other by this 1 over v squared term, then we have a wave.
Then we have a wave.
Mm-hmm.
Okay.
Okay. So next, let's talk about the speed of a transverse wave on a string. Speed of a wave on a string. I don't know. I don't want to bombard you guys too much. We have time. I don't want to cram pack this. Should we call it there? Do you feel like that was enough? Or you want to keep going?
Well, how close are we to being done with this section?
We're about halfway through.
That's
This is
it.
all good.
I
Well-
have some homework I want to go over.
Yeah, we'll call it there so that we have time to go over homework problems.
Can you do
So-
example problems?
I've done every example that's come up so far. Yeah. Next example problem, we need to go over the speed of a wave. So, we'll leave it there for now, and we'll continue with it tomorrow.